Tonight I want to talk about soil classification. A couple of things I want to point out, just as a quick refresher. This is what we call a particle size distribution graph, or a particle size distribution curve. These lines that go up and down, these lines each represent a soil sample. So I might say, have a look at soil F. And what I would mean is look at this line, okay? All right, so this is line F, okay? So that's what those lines mean. The other thing to point out is that this is what's called a semi-log plot, where the vertical axis here is a linear scale. That just means a normal scale. And this is percent finer by weight. That's what we do in these distribution curves. But the horizontal axis, that is a log scale. That's why we call this a semi-log plot. And you know, things to notice about a semi-log scale is that there is no zero. Things just get smaller and smaller and smaller, and this is a log base 10 scale. So every unit is 10 times larger than the next. And because of that sort of scaling of 10 times larger, 10 times larger, 10 times larger, it also means that the intermediate values on that curve are not evenly spaced, right? So for instance, if we go from here, it's 0.01, and then I go to 0.1, then I go to 1. Well, the size of this division is actually 10 times more than the size of this division. You know, so if this point that I'm pointing to right here is 0.01, then 0.02 would be this first line, quite a ways along. 0.03 is sort of approaching halfway, and then 0.04 is just beyond halfway, and then the other divisions get tighter and tighter and tighter. That's a log scale. And the cool thing about a log scale is that it allows us to put on huge size differences, right? So we can talk about microscopic particles down here, and we can talk about boulders at the other end, but they all fit on one scale, and they all have the same amount of, let's say, resolution, even though the scale is gigantic. Okay, so the log scale kind of zooms in on the little stuff and zooms out on the big stuff so that we can see everything. And that's very common in all soil mechanics and geotechnical engineering, because so many properties of soils span huge, we call it orders of magnitude. That just means like 10, 100, 1,000, 10,000. Those are orders of magnitude. Fancy word. The other thing I want to point out is on the top, we superimpose this scale that tells you where things start. Okay, the small stuff is down at this end. So here, we call this the fine grain soil. Remember, soil is either fine grain or coarse grain. Fine grain stuff is here, and the division line is the number 200 sieve, which corresponds to 0.075 millimeters particle size. So if you follow this line all the way down, you'd find that it crosses somewhere in here, which is 0.075 millimeters. And this is where we define silt and clay are on these sides. And then you can see sand and gravel. And the number 4 sieve is the division sand and gravel. That should be just a nice quick refresher. Someone says, why do some of them not start from 0%? Good question. So you'll see these lines, like some of these lines go all the way down to nothing. And what that means is that if there was a sieve test done on soil sample B, it means there was hardly any dust left passing the number 200 sieve. It was just a tiny amount, and they were able to just give 1 point and say, wow, we've accounted for the entire sample. We'd look at something like soil B, and we would say it's very clean. Something like soil D, we've done a test, and you have to do a hydrometer, right? So remember, the sieve is what we use for the coarse grain soil distribution data. And then the hydrometer is what we use for the fine grain soil. That's where we let the soil settle out of suspension. Well, I'll tell you what, there's some soils that takes so long for the particles to settle out of suspension that people just stop the test. And they say, well, okay, this is our last data point, and all we can tell you is that there's 20%, 22% more of that soil that was still in that solution that we just kind of didn't have time or patience to figure out what was in it. So there's more mass, but it was still left in the soil suspension, and maybe they left it for a few days and it still hadn't settled out. It just means that there's tiny, tiny fine particles floating around in there. So where these lines stop is kind of where the test stops. It doesn't mean that the sample doesn't exist. It does. It actually has to, right? So these lines, it's quite reasonable to be able to extrapolate these lines and say, well, we know that 22% is definitely finer, because this axis says percent finer by weight. So what you can say is that 22% of soil D was finer than 0.007 or something like that, and so that it's just where the test ended. That's the answer to your question, but it's a good question. I'll also note that, remember, this log scale doesn't ever go to zero in terms of size. And if you think about it, that makes sense, because what is a zero size particle? I don't know. Is that like a black hole? I don't know. It's a singularity, I guess that's what it is. So for particle size, it kind of makes sense for us to use a log scale. This is the plasticity chart, and this actually shows up in your Atterberg limit lab write-up for how you classify the type of fine-grained soil that you're testing. And it's the plot of your plasticity index, right? So your plasticity index is on the vertical scale. The plasticity index is the liquid limit minus the plastic limit is the plasticity index, okay, versus the liquid limit. And what you do is when you finish your Atterberg limits testing on a soil sample, you plot a point, and the point will fall somewhere. Maybe the point, I'll draw it. So let's say let's say the point falls here from your lab data. What that means is this soil is a CL. Okay, so because it falls inside, you see where the thick lines are. There's kind of a funny trapezoidal shape, and if your dot falls anywhere kind of in this region, that's going to be a CL. I mean, if I was really good, I could. That's not bad. Okay, so that region, that's all CL. Similarly, if you plot up here somewhere, that's going to be a CH. Plot down here, it's an ML. Over here, it's an MH. Yeah, someone said, well, what if something's on the border? That's always a problem. It's unusual you'll get something right on the border, and if you do find something on the border, you could always go back to the hydrometer and say what the percentage is, because I'll tell you what, this A line, the A line is the theoretical, or actually it's not really theoretical, it's sort of experimentally derived division between clay, right? And clays are here, and silts. The silts are down here. Okay, so there's also funny spots, so it's a good thing to point out. If you happen to have a soil that's down here, this is a funny little tiny region, and it is possible to get soils in this region where you would give them a different two-letter code. And let me just define what these letter codes mean. And this is kind of the beginning of what we're doing tonight, surrounding the Unified Soil Classification two-letter code system. So in the two-letter codes, we're going to use the letter C, and we're going to use the letter C to indicate clay. Okay, I know I'm right on the border there. I'll move a little bit. So C means clay. M means silt. And I think S doesn't mean silt because S means sand, which we'll get to later. So S was already kind of taken. So we use M for silt. H means high plasticity, and L means low plasticity. Okay, so we'll for fine-grained soils, these sort of letter codes have these meanings. Okay, and so if you look at this, and you say, oh, we've got a CH, like a CH is a high plasticity clay, and MH is a high plasticity silt, et cetera, et cetera. Okay, so that's what those mean. On this curve, the A line, like I said, is the division between silt and clay, C's and M's, and the U line is sort of, we don't observe values above the U line. The U line's kind of like, if you get a number above the U line, maybe you made a mistake doing your lab and you better go back and check it, because properly done tests do not plot above the U line. So that's what that means. And just a quick note too, the liquid limit and plastic limit, those are a number, but the number is actually the water content. And I hope everyone remembers the formula for water content, right? So mass of water divided by mass of solids, right? So even though we express it as a kind of percentage, I said last class it's really better thought of as a ratio. It's a ratio of the mass of water to the mass of solid, or the weight of water to the weight of solid. Same thing. Okay, so that's how we use the Atterberg limits to determine these two-letter codes that we're going to get into a little bit more tonight. Okay. The other thing I wanted to sort of refresh your memory on was these two CU and CC. That's the coefficient of uniformity and the coefficient of curvature. And for these two, I guess, formulas, for lack of a better term, you need to be able to read off the diameter at which the curve for the soil crosses either the 10% passing, 30% passing, or 60% passing. And that's indicated by the green lines on this curve. You can't see through this one because I just copied this from last week's slides. But just as a sort of a sample, I put some of the numbers. And I think the D10 we kind of debated a bit, and maybe the D10 should be 0.013 or 0.012, something like that. I can't remember. But basically, we're going to need this for what is also what's coming later. I might even just jot them down. I'll put them over here. So just remember that CU, coefficient of uniformity, is D60 over D10. And coefficient of curvature is D30 squared over D60 times D10. Okay, so I'm just collecting the things that we're going to need. So the first thing, you can't read this. I can't read it, but I zoomed back out on this flow chart because this is what I want to actually work on tonight. One of the things I want to do tonight. This kind of complicated chart is the chart for classifying and giving what we call a group name to a soil sample. And this particular chart is for fine-grained soils, okay? And how do we determine if something is a fine-grained soil? And the definition is actually right up here in the name of the chart. So it says flow chart for classification of inorganic fine-grained soil, and in brackets it says greater than 50% passing the number 200 sieve. So in essence, the definition of a fine-grained soil is something that if I look at the curve for that particular soil sample, and I look to the number 200 sieve cutoff, and I come down here to 50%, it looks like I have 3 soil samples that have a line above 50% at the number 200 crossing line. So soil A, soil E, and soil D appeared to be all fine, what we would classify as a fine-grained soil. And that's the first lesson in tonight's classification, is to how do we decide if it's a coarse-grained or a fine-grained soil? And it's really that 50% line combined with the number 200. Okay, so, and we would classify them using this particular flowchart. Okay, and we'll go into, there's some nuances to this flowchart that we'll actually get into. So first assume that we're going to look at one of those three soils because they're the only ones that would apply to this, the classification of so-called inorganic fine-grained soil, basically silt and clay. So the first choice that we have, and I think you can read this, the first choice, once you've identified the soil as fine grain, is we use the liquid limit. We use the liquid limit as the deciding factor for the first decision in this classification system. So if our liquid limit is, let's just say hypothetically, our liquid limit is below 50, then we're going to follow the flow chart in this direction. Otherwise, we follow the flow chart in this direction. Okay, not too difficult really. And then let's just say we carry on in this part of the flow chart with our liquid limit less than 50. The next thing we do is we have to identify that two-letter code, right? And that two-letter code we call the group symbol, and the group symbol is coming from that chart that I talked about before. This one. Okay, so we're in the classification process, and we reach the decision point of, okay, where does it fall on this figure? We call it figure 5.4 in this particular text. So we get to this figure 5.4, and that's coming from, the data is coming from the liquid limit, plastic limit, and plasticity index, which is just liquid limit minus plastic limit. So then we give it either a CL, a CL slash ML, or an ML. And notice that I'm not going to get an H in here anyway because my liquid limit is less than 50. So it's if I have a liquid limit less than 50 and my soil plots in a quadrant that's not one of these quadrants, then I've done something wrong. Okay. So that's the first step. The next step, depending on which one of these we fall into, we then go over and say, is it greater than 70% silt and clay, or is it between 50 and 69%? Same decision for each of these other ones. Notice that the lower limit is 50%, not 0, because in order to be using this chart, it has to be greater than 50%. Okay, so pretty logical, sort of how you find your way through this, I hope, anyway, so far. And then let's say we come to this decision tree where we go, let's say it's greater than 70% passing the number 200. Then we ask another question, is it greater than 85% passing the number 200, or is it between 70 and 84%? And then if it is between 70 and 84%, we have another decision to make, and that is the percentage sand greater than or equal to the percentage gravel, or is the percent sand less than the percent gravel? Okay, and so you need to follow these greater than or equal to sort of flow charts, pretty easy really. And then the last part of the graph, after you've identified what percent sand versus gravel, or specifically a percentage of sand or gravel, we can then actually assign the so-called group name. But you can see some of the names that we end up with. You know, we can end up with a lean clay with sand, lean clay with gravel, sandy lean clay. But notice that the noun is always a clay. So it kind of it should remind you of the soil descriptions that we had from before. That those soil descriptions from last week actually came from the Canadian Geotechnical Manual, primarily used for sort of a quicker classification. The Unified Soil Classification System has a little bit more detail to the actual so-called official group name, and it's good for you to do this. This is another flow chart that I want you to ignore, and you might say, well, that's good. And that's because this is for organic soils. And in my practice in geotechnical engineering, we usually would stay away from organic soils. So they're not really something you want to build with. just know that it's here. And the Unified Soil Classification System does deal with the classification of organics, but we're not going to focus on them. But what we are going to focus on is coarse grained soils. And again, I know you can't read this, so let's just step through how you classify a coarse grained soil. And that would be a soil that has greater than 50% larger than the number 200 sieve. Okay, so it's the reverse from the first fine grain example. A couple of things to note. The first thing that we do in classifying a coarse grained soil is we decide, is it gravel or is it sand? And we do that by saying, is the fraction of sand less than the fraction of gravel? Okay, that's, and I'll tell you what, there's a couple of other words up here. I should define the S. We're going to use S to mean sand. We're going to use G to mean gravel. We're going to use W to mean well graded, and we're going to use P to mean poorly graded. Right, and remember, we're going to use the geotechnical engineering meaning of the word well graded and poorly graded, where well graded means that it has a lot of different particle sizes. Poorly graded means that it's kind of all one size. Right? So poorly graded would be like that bag of marbles. Well graded would be like a gravel that you want to pack very tightly, that has a wide range of particle sizes. Okay, so again, pretty straightforward, but these are the letters that you're going to see showing up here. So after we've determined the fraction of gravel versus the fraction of sand, we then go down again through the grain size distribution and say, well, is it less than 5% fine grain soil, or is it between 5 and 12% fine grain soil? That's what the number 200 means. Or is it greater than 12% fine grain soil? And then depending on what it says, so notice down here, well, for both of these, there's a significant portion of fine grain soil. So down here, you'll still have to classify the fine grain soil as an ML or MH or CH or CL or CL, sort of like you did for classifying fine grain soil, which means you need to run an Atterberg limits test on the percent that passed the number 200, right? So in the lab test, you would need to actually do that. If for these two divisions, we actually have to calculate the coefficient of uniformity and the coefficient of curvature, because that's our next dividing line here in the flowchart. Okay, so you have to be able to calculate those numbers to follow along. And then here, there's even a second check. You know, we have to do the coefficient of uniformity, and then we have to do the coefficient of curvature. And same thing here, coefficient of uniformity, coefficient of curvature. Down here, we just need the uniformity. We don't need the other one. And there is even a little zone here where they cross over. Okay. And then the last sort of part I zoomed in on is just where it gives you the group symbol, the two-letter code, and the group name.